Can you declare which chats here, right?
The lives.
Okay. How many are there now?
Yes.
Only one have joined. One has joined till now. Yeah. So let's wait 1, 2 minutes, 2 or 3 minutes more. Maybe some more joins, and we'll start our discussion. In the meantime, I could reply to this. Yes. No, because this gentleman may not be here. He's a rocket professional. We send a message that live class has started. People might join. Could we send a message that live class has started? Because it's already 5 minutes past.
Hello. Hello.
Yeah. Hello. Hello. Please unmute yourself.
Hello. Good afternoon, sir.
Very good afternoon. You are Vishwas?
Yes, sir. I'm B. Vishwas.
Please. Yeah, please. You
Sir,
have
I
any
have just
specific
one
questions,
question.
please? Please.
Where is the application of this monoclinic material?
Monoclinic material. As such, you will not find any application in monoclinic material. Okay, at least I'm not aware. I mean, because as you see, monoclinic materials are they are naturally available. Some of the materials, like I have already given some examples, right? But as far as the structural application is concerned, I'm not aware. I don't think there is any.
Okay.
Because if we appreciate this course, in this composite course, we are trying to basically in these FRP composites, the anisotropy is advantageously used. Okay, therefore, what we have been discussing actually is orthotropic composites, right? All these lamina are actually orthotropic composites. Like it has two mutually perpendicular planes of material property symmetry, and of course that automatically guarantees that there is third plane also. And those orthotropic materials we are actually advantageously used because of two reasons. Number one, they are inherently lighter materials. Number two, they are very strong and stiff, and we can actually impart direction dependent stiffness and strength according to our requirement, according to the design requirement. Okay, that's why they are advantageously used in structural components. Yeah, please, any other question, please go ahead.
And regarding the, we have defined initially in the anisotropic material, we have defined the 81 constant. Then
Right.
we have reduced it to 36 constant.
Right.
Is there any application of these constants in the software? Do they make use of these constants while doing the programming for FEA softwares like LS Dyna and ANSYS?
Yes, yes. See, basically in 3 dimensions, I think I can go a little bit more into that at a point. Actually, depending upon the plane passing through that point, there could be infinite planes. And if you if you remember that the stress will be different in different planes. I think a little bit I have discussed also, but you can just go through any strength of material book. But what happens is that if we can define the stresses with respect to 3 mutually perpendicular planes at a particular point, then by Cauchy's rule, we can actually find out the stress in any other inclined plane. From there, it comes that there's 9 components. So in 3 mutually perpendicular planes, in each plane, there could be 3 possible stresses. What are those? One is normal stress, which is perpendicular to the plane, and 2 stresses which are along the plane in mutually perpendicular directions. Therefore, 1 normal stress, 2 shear stresses in each plane. Therefore, in 3 mutually perpendicular planes, we have 9 stress components. Is that clear?
Yes, sir. Yes.
Or I can draw also if you want, but it is available in any strength of material textbook. Therefore, 9 stress components, and there will be corresponding 9 strains. Okay. So as I have mentioned briefly, that this is actually second order tensor, and these stresses are actually related to the strains by means of 9 cross 9, so 81 elastic constants. Okay. Now from there we understood why 36, because for symmetric stress tensor, like what is symmetric stress tensor? Again, that also I have discussed very briefly, that equilibrium cross shear tau xy is equal to tau yx, tau xz is equal to tau zx, tau yz is equal to tau zy. That comes from the condition of actually rotational equilibrium. However, there is a constraint that this is true only in the absence of body moment. Okay, suppose there is a body moment like magnetic moments, then it is not true. Other than that, in most of the structural applications where body moment is absent, equality of cross shear holds good. Therefore, immediately from 9 stress components, it becomes 6. So 6 stresses, 6 strains. Therefore, they are related by 36 elastic constants. And then we understood from the concept of energy, that concept of strain energy density function. We have proved that for those kind of material, that actually the stiffness matrix is also symmetric, and therefore we need actually 21 independent elastic constants. And so we say that these 21 independent elastic constants are for anisotropic, because we have not talked anything about the planes of material property symmetry. And then further we have shown how it gets reduced, finally comes to 2 for isotropic. But your question that what we do with these elastic constants, correct? If I understood, that is what your question was, right?
Yes, yes.
Yeah. So now what happens is whenever we do stress analysis, suppose given a load, what we do? Given a load, we find out the stress. Given the stress, we try to find out the strains. Okay. And for that, basically that is the property of the material. For that, we must know this elastic constant, that C matrix. Okay. Given the stresses, we can find out the strain. If I know this C matrix, that means the elements of those C matrix or S matrix, vice versa. Okay. So for any finite element programming, that is very, very important. We have to do that. And that is what, if you remember in finite element analysis, basically if in displacement based finite element analysis, what we find out is we immediately find out the stiffness matrix, because finally we put this in the form of Kx equal to F for static analysis. K is the stiffness, X is the nodal displacement, F is the nodal forces. Okay, so that K actually comes from these material properties. Okay, this K for a given structure actually depends upon that stiffness, which is the property of the matrix, as well as the dimensions. Okay, therefore, without those C or S matrix, you cannot do any analysis. So these are these are required for any stress analysis applications. Whether it is finite element, even for if you want to do analytically, that is required.
Okay, thank you, thank you.
Could I reply question? Otherwise, I could write also if you want me to write, but because it is in the textbook,
No, sir,
I thought of not
clear.
writing.
It's clear, sir. I got
yeah.
my answer. I got the answer to my question. I had the confusion that whether whatever stiffness matrix we use in FEA and whatever stiffness matrix you explained, I wanted to know whether both are same.
See, there are two different. No, I'll tell you, please. Suppose if you take a rod, axial bar, okay? For an axial bar, if you want to do a finite element analysis, if you take a bar element, you will find that there is a stiffness matrix, okay? So that is actually EA by L. Now, E is the material property. I think I told that also a little, if you just see the videos carefully, that stiffness of a component is actually a function of its material properties. Say in this case, if it's an axial rod, it's only Young's modulus, okay? And the length and the cross-sectional dimension, okay? So similarly, in finite element analysis, whatever K matrix we finally form for an element, whatever the global K matrix, that includes the material properties. Along with that, the dimensions are there. You can see for a beam element, what is the stiffness matrix? You can clearly see all these dimensions also come there. In addition to those properties like Young's modulus, Poisson's ratio, rigidity modulus, those will be there. Along with that, the dimension will also be there. So the stiffness matrix in finite element, what you see when you write finally K x equal to F, that K actually, each element of K actually includes the term, which are the material properties as well as the dimensions of that particular structure. Is that clear?
Clear, sir. Thank you.
Yeah. Hello, who is the Shubhalakshmi? Is there any, what is your question, please? Or it's in chat only? Okay. Okay. I mean, maybe regarding FRP rebar, I think I'll give you the good source. I'll search and I'll give you a good source. I mean, what exactly you want to know in FRP rebar, I'll send across the source by email. Okay. Any other question, please?
Sir, I have just one request.
Sure, please.
Yeah, I've gone through the content of the course. Can you, in the end of the course or at the end of any lecture, can you just add if we are doing the literature review to select the matrix and fiber for the new research? So what factors we have to consider from the literature? Because there are many journal papers which have used lot of fibers and matrix. If I want to do research in composite materials, what factors I have to consider to select or what is the research gap in composite materials?
Okay. So I think in the first module, in the introduction, I think briefly the types of fibers and the types of matrix are actually introduced very briefly, of course. Now, and their relative merits and demerits were also it is discussed in very brief. Okay. However, like I understood, if I understood your question correctly, what are the factors based on which you will decide what kind of fiber or what kind of matrix you will select? Is that your question?
Yes, yes.
So I think we have already addressed in this course like why we go for polymer matrix composite, and when we go for metal matrix composite, when we go for ceramic matrix composite. I think that is there in that course. But if you really want to know details on the matrix, like based on what are the properties, what are the other physical or chemical properties of what are the different grades of polymers, because there are wide different grades of polymer matrix are also available. You may please go through some of the handbooks, okay, or even in some of these textbooks also it is there. Polymer matrix, defined polymer matrix which are available, like whether we should use phenolic resin, whether we should use epoxy resin, thermoset, thermoplastics. So you can go through some of the handbooks. I think one handbooks I have already replied to some of them by Lubin, George Lubin, CRC Press. You just send me a mail. I'll give you the details of the books. If you are interested, you can go through those. Okay.
Okay. Thank you. Thank you. Sir, one last question. Which software is suitable for finite element analysis of composite materials?
If software.
Yes, if I am supposed to use a new software, should I go for LS Dyna? Should I go for ANSYS or Abacus? Many softwares are there. Which software do you suggest for research purpose? I have to learn.
No, suppose you have access to all of this, then I can tell you, like, it is actually nothing like that which software is best for composites. In my opinion, it's not like that, because finite element as a tool, okay, you can use. Now, yes, there are some issues. That's my personal experience, that some of the modules are good in Abacus, some of the modules are good in ANSYS, but that's not absolute. Okay, if you just want to start finite element analysis of FRP composites, if you have access to ANSYS, if you have access to Abacus, I think both are good enough. You can start with one of them. There's okay, either of these is perfectly fine for preliminary analysis of FRP composite structures.
Okay,
because
thank you.
It depends. If you have already ANSYS, you can start with that. If you have already Abacus, you can start with that. Okay, because only when you actually go for some critical, very like say somebody is interested to do say high velocity impact, then sometimes maybe one particular software has certain edge over others. Otherwise, in general, for structure analysis, especially for static and dynamics routine analysis, I think most of them are fine. There is no issue in that. No one else has joined yet. Some of them are writing this, like Subhalakshmi. FRP, but that I have already replied. I'll find out some source because I'm not much conversant with these civil engineering applications. So, but I know that FRP reverts are actually used. But then, okay, I'll see if there is a good source, and I'll send you. I'll write you back. Who asked about how to analyze the impact of high temperature and pressure on laminate properties for glass reinforced? Impact of high temperature and pressure. Vijay Ketkar, are you online? Are you online? Like, if you want to know the influence of temperature and pressure in the manufacturing of composites. So again, because in this course we have been only discussing the mechanics. However, you can go through any of these books where the manufacturing details are there. The whole curing cycle and the influence of different temperatures and pressure in the curing cycle and the final properties are also described. So you may go through any one of these handbooks, or even I think I have replied to some of the questions in the like a book by PK Malik is also good. You can just go. There is a brief description. If you go through that, brief descriptions on the composite manufacturing and how the curing cycles, all those details are actually there. You may go through that. Okay. Is Rathi's channel is please be specific what basics, because I only told that it requires the basic strength of material, and the very basics of that I have already discussed in the brief review of elasticity. However, anyone who is having a civil engineering or mechanical engineering background might have done those courses. But if you still feel that you need to go through, then you can go through any book on strength of material, like maybe Shames or Beer and Johnston, or maybe any other standard textbook. Okay, strength of material. That is what is what is required actually. Mhm. Any question? Any other question from anyone? I could see someone else have joined. Lokesh.
Sir, I want to study anisotropy, so I want to know any good book regarding.
What? Could you repeat, please?
Anisotropy.
Anisotropy.
Anisotropy. I want to study more about it.
Anisotropy, elasticity.
Elasticity.
So, yeah. So if you want to know, if you have done courses on isotropic elasticity, so there is a good book by Leknevsky. Okay, I'll do one thing. I'll give you the exact name and that publisher also. Please post a mail. Okay.
Okay.
So that I can. Leknevsky is a good book. I'm not sure whether reprint is available, but I'll send you the exact name. Okay.
Okay.
Name and publishers.
Excuse me, sir.
Please go ahead.
Sir, can you provide PPT or any course material for this? It will be easy for us.
I'm sure. I think the course material will be there after some time, but PPT I'm not sure. I'll have to discuss with NPTEL.
Okay.
Is there any provision for providing PPT or not? Because
at least if you provide course material, it will be useful for us.
Okay. Let me see, because I'll have to discuss. I'll have to find out for NPTEL. But most probably there is a provision for course material. Yeah. So yeah. I'll just find out with NPTEL. Yeah. Course material must be there. Yeah.
Okay. Excuse me, sir.
Please.
Sir, is there any way to remember a shortcut for transform reduced stiffness matrix? Any shortcut, sir? Because it's very difficult to remember such a big formula. Q bar 1, Q bar.
Oh, yeah, no. See, make sure one thing, you don't have to remember those formula. It is not that easy to remember. Why should you remember?
Because questions will be based on that, no? Problems will be.
No. I don't think. See, if you look at the whole objective of this course, it's mechanics of composite material, not to test how many big formulas you can remember. No, it's not. If those formula, whenever it is required, that will be made available.
Okay.
You don't have to remember all this cos to the power 4 theta, sin to the power 4 theta. It's not required. Okay.
Okay.
You make sure that you don't need those things. Okay.
Okay.
In assignments, the questions will be there because you have the books with you. Okay.
Okay.
But no, in exam, the thrust is not to see that how many big formula you can actually remember. No. Okay.
Okay, sir. Thank you.
You have to only remember very basic formula. See, these things are like Hooke's law. That everybody anyway remembers. Okay. So those are the. Otherwise, you don't have to remember those formula. Big formula. Any other question from anyone who is there in the meeting?
No, sir, no question.
Lokesh, Mr. Lokesh, any question from your side?
No question, sir, but a request is that after this course, if you focus on structure also for composites, it will be better for us, sir, to know complete about the composites.
What is your background actually? You are
basically I'm mechanical engineer, sir.
okay.
I'm a faculty in Malad Engineering College, Hassan in Karnataka, sir.
Oh, I know Malad, yeah. And you have done your masters also? Yeah,
I've done my masters. I'm doing PhD now on coating.
Okay. So in my masters, you had any course on composites?
Yeah, composites I had.
So then you know most of this, okay?
Oh, so, most of the things I know, sir.
Yeah, but you are asking for anisotropic elasticity.
For the study to know. Yeah.
Yeah. So anisotropic elasticity, whatever is required for this course, I have already told you. But beyond that, as I told you, there is a book which I'll give you. Like this book, I'll give you the.
I have already emailed, sir. I already emailed.
Okay. Okay.
Please continue this course for structure also, sir.
Okay.
Any new course? Okay.
Okay. Let me first.
And also, if you have FEM along with the composite, it will be very abacus or something like that.
Okay. You mean application of FEA in composites?
Yeah.
Okay. Okay. I'll see. Any other? Yeah. Thank you. Any other question?
Thank you.
Okay. I could see another participant. What is Debabrata?
Yes, sir. Can you hear me?
Yeah. I could hear you. Please.
Sir, actually, I'm from a different background. It's mine is BSc Textiles and Clothing, sir. I'm from arts background. So I have taken this as one of my PhD online course. It's mandatory here.
Okay.
So I need to complete this, but first unit it was very easy. I was able to follow from the second and third unit. I mean, second and third week lectures. I'm not able to follow much because it was completely different. I don't know about matrix, compliance matrix, and other things. Even Young's modulus, I have a big gap. Actually, nearly around 20 years after my UG and PG. So I have come for PhD. So it's very difficult for me to follow from the second and third unit onwards, like unit in the week onwards. Second unit also I am able to yes sir. I went to YouTube channels and found what is Young's modulus and other things, and remaining like anisotropic and I have not at all heard. So since I have taken my PhD topic related to composites, acoustic composites, I have taken this as one of my subjects, and I thought of taking the introduction to composite. It was not there, and even manufacturing was not there. Only this is available in NPTEL. So I took. So I find it very difficult to follow. So whether there will be any basic books related to that, so that I can study and learn about the basics and then follow the remaining things. Will it be easy, sir? I don't know about this subject.
No, I understand. I understand completely. So actually, a basic course on first course on strength of material would make things easier. But since you have not done that course, because as this is the course is on mechanics of composite materials, it is mostly based on those stress-strain relationship. And since you have not done that course earlier, so you may, I clearly understand there will be little difficult on your part in that case, because in that case you may try with a basic strength of material book. If you could revise, then you can actually come to that. Actually, if you know the stress-strain relationship, Hello.
Yes, sir. Yes, sir. In between there was a break. That's why I'm asking. Now it's okay, sir.
So if you could understand the basic stress strain relationship for isotropic materials, which is taught in any university for civil or mechanical engineering as a first course, then it will be easier. Okay. Having not done that, maybe you can just take a book on strength of material and go through the first 1 or 2 chapters where they talk about.
Actually, there was one more course about nature of materials. In the last live session, someone suggested me there was in the same NPTL. It is related to nature and properties of the material. Will that be? I have registered on that after his suggestion. Will that be best for me, sir, to learn about the basic nature and properties of material? And one more thing, sir, and there is 2 more subjects like manufacturing and introduction, isn't it, sir? Shall I take the videos of that, and if I study that, will it be easy for me to follow this one?
Manufacturing is not required in this course.
Okay.
In this course,
introduction to composites.
Only first is it is only mechanics. Basically, with an objective to understand the basics of design of components made of this fiber reinforced polymer matrix composite structures. So manufacturing is not required, but yes, material characteristics is required. I'm not sure the course you are talking what you are talking about because
in the NPTL itself.
I understand, but what I suggest is basic strength of material book. You see, if you could see the first 2 chapters where they talk about stresses, strains, and the relationship, and based on that you can actually build up. Okay,
sir. It is. Is there any specific book related to this, sir?
I would suggest BR and Johnston. If you that would be easier to follow.
Can you type it, sir? I could not make the spelling.
Then you just send me an email so that I will type everything correctly with the publishers also.
Okay, sir. In which mail should I put, sir? Is there any?
No, there is a question. This thing, no, there itself you can type. I have already given it to someone. I'll just. You are not in that question thing. There is a provision. No, you can ask questions.
In the NPTL, sir.
In the
NPTL. Yes, sir. Yes, sir.
So you just send drop a mail. I'll reply back immediately.
Okay, sir. Okay, sir. Thank you, sir.
Yeah, welcome.
Somebody has suggested mechanics of deformable solids. Is it for me, sir?
No.
Mechanics of deformable.
It's for you. It's for you only, madam. E-copy is available. E-copy is available. It's good.
Okay, sir. Okay, sir. Thank you, sir.
Vinod Kumar, could you be online? I am not clear about what you have asked. Simulate and relate with our theoretical understanding. Could you be online and so that we could have a meaningful discussion on what you exactly want, and maybe I could clarify your. Vinod Kumar.
Will this section be available every week, sir, or only for this week, sir?
Pardon?
Will this session be? Will you be coming again? Because today only my exams got over. For the from the second week onwards, I have to make a thorough study. If I have any doubts, whether you will be available to.
There will be more
sir?
sessions. There will be at least 3 more live sessions.
Okay, sir. Thank you, sir.
Yeah. Okay. Vinod Kumar. Yeah, regarding your question, FE analysis of composite laminates, maybe using ANSYS. Actually, that is not in the scope of this course. However, if you have any specific queries, yeah, you may ask. I'll try to reply to your queries. I mean, extensively used. FEA softwares are extensively used for analysis of composite structures. So if you are also using, if you have any specific queries, I'll try to reply to your queries. You may please put your queries, but not in this course. I mean, it is not in the scope of this course. I think it's disconnected, no? Chat. It's showing that unable to connect. No, because it's 4, maybe. Is it because of that?
So distant.
Oh, no, it's okay. Thank you, because time is over. We'll sign off today. Maybe next session. Yeah, you are most welcome.